What's going on, you guys? So today we're going to convert a sorted array to a binary search tree. So we're given an array where elements are sorted in ascending order, convert it to a height balanced BST. For this problem, a height balanced binary tree is defined as a binary tree in which the depth of the two subtrees of every node never differ by more than one. So every single node, every time we branch, that creates a new mini binary search tree. So here's the example we're given. -10, -3, 0, 5, 9. One possible answer is 0, -3, 9. -10, null, 5. Okay, so each node, so we're creating one big binary search tree, and each node of that binary search tree is also a binary search tree. So it's a recursive function. Well, we can think about it as a recursive function, where we're taking an array, we're setting a, so we want to balance each side. So how can we do that? Let's think about this array. Okay, so we want to balance this. There's 1, 2, 3, 4, 5 elements. So we want to set 2 elements on each side. And with a binary search tree, all elements to the left of a node have to be less than, and all elements to the right have to be greater than. So we have a sorted array, so we know that the midpoint, everything to the right of the midpoint is going to be greater than, and everything to the left is going to be less than. So we can set the midpoint equal to the root, and then we can recursively create another tree on the left and another one on the right with the remaining values. So let's think about how we would do that for this example here. So we're going to start off calling our recursive function on the whole array. So we're going to find the midpoint, which we can just so let's see here. 1, 2, 3, 4, 5. So we can divide the size by 2, which will equal 2 in integer division. So 0, 1, 2. It'll set this value equal to the midpoint. And then we're going to recursively call the same function with all the values on the left for our left subtree, and we'll call with the values on the right for our right subtree. So, okay, let's move on. So recursive -10, -3, so size, so 2 divided by 2, we're going to set 1, 0, 1 equal to the midpoint, -3. We'll recursively call to the left with all the values to the left and all the values to the right. And on the right there are no values, so we'll return null when we pass an empty array. And likewise for the right side of our BST, we're going to take the size 2 divided by 2, which is 1. So we're going to set the 1 index to the root node of this BST, and we're going to recursively call with values on the left and values on the right. So that's the idea behind our approach for this problem. So let's write that out. So we'll find a midpoint and set to root. Set root dot left to recursive of left values. We'll set root dot right to recursive of right values. Okay, and then we'll return the root. So let's think about time and space complexity of this. So let's think. So it's going to call recursive. So space complexity, each time the nums array that we're calling it with is getting cut in half. So we'll call our recursive function log n times. So that's our space complexity. Let's think. Let's take a look at our graph again. So we end up calling, let's see. So we call recursive for each value in our array. So this is going to be O of n runtime and O of log n space complexity. Let's think about that. So each recursive call creates 2 additional recursive calls. So let's think. So we start off with the full array. We look at each half. So this call creates these 2 calls. But we're dividing the search space in half each time. Okay, I'm sticking with log n for space complexity and O of n runtime. Let's implement this in Kotlin. So what are we going to do? Okay, so we want to find the midpoint. So our midpoint is just going to be, first off, we need to create a helper function. So we'll call it recursive. And it's going to take nums, which will be an int array, and it'll take a left index of nums and a right index of nums. So this will help us define our smaller search space on each iteration of recursive calls, right? Because it starts as the whole thing, then we look at the right half, then the left half. So we want to be able to define which part of the nums array we're going to be looking at. So we'll do that with these variables. Okay. Int, we'll call it right. This will be an int. And it's going to return a tree node. Okay. And in terms of edge cases, if nums.size is 0, we'll just return 0. And we're going to return recursive. We're going to give it nums 0 and nums.size -1 to start. And so what's our stopping condition? Our stopping condition, so we're moving our left and right. We're moving our left and right indexes closer and closer together to each other. So eventually they're going to converge. And so when we want to return null when we get to this situation. Or let's think, what are we going to return? Yeah, so this is nullable. And let's see, so if left is greater than right, we'll return null. That'll be our stopping condition. And this is going to be null. Okay. And so we're going to compute midpoint. And this is going to be left plus right over 2. But we're going to do a little trick. So to avoid integer overflow, rather than adding two potentially large numbers here, we're going to do this. We're going to say we're going to subtract two potentially large numbers. Okay, so that's our midpoint. I'm going to say we're going to set our root, and it's going to be a tree node of nums mid. And we're going to set root.left equal to recursive nums, and root.right. Okay, so let's think about what will our bounds be. So on the left subtree, we want to give it all of the values to the left of the midpoint, right? So all the values to the left of 0. On the right subtree, we want to give it everything to the right of our midpoint. So what are all values to the left? From left, which is our original left boundary, we're going to give it mid minus 1. So in this case, mid is 0, 1, 2. So we're going to go from 0 and 1. These will be our boundaries for the left. And for the right, it's going to be mid plus 1 to the last value. So this one will be mid plus 1 to right. And then we're going to return root. And as you can see here, eventually these left and right values are going to cross as they're getting closer and closer to each other. And then once they do, like let's think about what happens here. So here we're giving this one left in this case is going to be so right here is 1. Midpoint is 1. So we're going to give it mid plus 1 is going to be 2. And we're going to give it a right of 1. So in this case, so left equals 2, right equals 1. Left is greater than right, so it's going to return null. So this checks out for our base case. Okay, so all right, let's check this out. Give it a shot. Okay, there you go, guys. And so going back to the space and time complexity, let's see. So for every value in the tree, we're calling recursive. And recursive is doing a few calculations which probably take, well, they don't take constant time because each recursive call creates 2 more recursive calls. So but if we're thinking about the whole array, so there's 1, 2, 3, 4, 5 elements in the array. And we call recursive 1, 2, 3, 4, 5, plus some constants. So when we give recursive like an array with values in it, okay. So it's basically O of n time, right? We're calling recursive 7 times. for an array of size 5. But 2 of them are going to be returning null right away, right? So basically we're calling it five times where we have to do some real work. So our time is going to be proportional to the number of elements in nums. And we're calling recursive 7 times here. I'm going to update this. I'm going to say this is O of n space complexity 2, right? Because we're calling recursive for each value in our array. Plus 2 more. O of n plus 2 is just O of n. Okay, so if you guys have anything different for space and time complexity, let me know in the comments. This has been convert sorted array to binary search tree. See you guys.